All right, guys, welcome to another episode of CUDA Education. Today we have a lot to go over, and it's a lot of moving parts. So you guys really have to uh, pay attention with this video. There's a lot of moving parts, a lot of things happening. We're still on the pipeline cache discussion, and we're trying to tinker with it and understand it a little bit better. So there's a lot of moving parts, so you really have to pay attention to this video and also, watch the whole video, so you kind of don't get confused as we go from one step to the next. All right. So we are on our compute headless algorithm where basically we run we input an array of 32 numbers. On the CPU side, we send it to the GPU. The GPU does some Fibonacci calculations and gives us a result from those calculations on the shader side. As we could see here, this is all the shader, headless.comp on the shader side, and we output basically Fibonacci numbers from the from what we inputted, okay, and we get a result. So the GPU gives us a result. Remember, this is compute headless, so we have no graphics capabilities. This is strictly a compute example. So we get these results. We from the GPU, we basically transfer over these results back from the GPU to the CPU, and then we display them to the screen as we have right here. Okay, so the battle that we're trying to fight today is basically this idea of a pipeline cache. Okay, so what we're doing is we're in our algorithm where we're creating a pipeline and we're saving the pipeline to disk, so that basically that pipeline with sort of all of its stuff and dependencies and stuff and the spare V and everything, it's boiled down to machine code, and we save that machine code on disk, so that when we need to re-engage with that pipeline with that particular set of specialization constants, etc., we could just read from disk instead of having to go through the expensive task of recompiling the pipeline and recreating the pipeline. Okay, so that is the battle that we're tackling. We are saving a file to disk, and then we're reloading that file from disk and running that file, that pipeline, and seeing our results. Now, one of the things that you have to understand with this line of logic that we're going through, just understand that for, let's say, the first, let's say for the first three inputs, right? For the first three inputs, the first couple of inputs, notice that the outputs is very similar. Okay, so we input 0, we get 0. We input 1, we get 1. We input 2, we get 1, which is a slight variation of what the input was. For 3, we get 2, which is still a slight variation, and so forth, right? So the first couple of inputs, notice that the outputs are similar. I mean, really and truly, it's just 0 and 1, but like I'm just going to extend it to 2, right? It's similar. It's not the same, but it's similar, okay? This is going to be very important later on in the video. It's going to be very important. It's actually a source of confusion for me, which is why I kind of threw out the Fibonacci calculation, you know, later on in the video. I throw this out to prove a point, but um, I don't want to get too deep into it right now. But just understand that, like, for the first couple of numbers, the output is very similar, and this has something to do with the cache and how the driver deals with whether it needs to um, create a new cache or basically run with the cache that we already have saved to our file system. I'll repeat. this issue right here, where the input and the outputs is similar, um, creates a problem for us, because if the driver deems that our pipeline that we already saved, the pipeline blob or the bin file that we already saved, if that saved version of the pipeline can make do, if it's sort of a generic version of the pipeline and it only requires slight modifications, the driver is going to say, okay, I'm not going to invalidate this particular pipeline. I'm going to run with it, and maybe make particular changes at runtime. Don't ask me why this is the way it is, but what happens is that, you know I save a particular pipeline with a particular set of specialization constants, a particular configuration. Okay, let's just leave it at that. I save the pipeline with a particular set of configuration settings, right? I save it to disk, and then in another script, I basically say, hey, Vulkan, load this pipeline from disk and run with it. Okay, so if the settings that I request in my algorithm is exactly the same as the settings that was in the saved pipeline iteration, the saved pipeline on disk, then we have no problem. The saved pipeline and what I'm requesting in my algorithm is exactly the same, so all is well. The pipeline, the algorithm says, listen, the saved pipeline is exactly what you're asking for in this run of the application. So I'm going to take the shortcut of pulling the pipeline from saved disk and using that to run the application and run our results and all of that good stuff. Everyone is on the same page, everyone is happy, there is no problem. Okay, and the way how Vulkan works is that even if you're pulling a saved pipeline, you still have to pretend like you're creating a pipeline, right? So you basically run the logic like you're creating a pipeline, and then what happens is Vulkan would say, okay, this particular set of configurations, this particular set of parameters that you have is matches up with a saved pipeline cache that I have on disk, right? So I'm just gonna do the shortcut. Instead of recreating the pipeline and all of that stuff, I'm just gonna pull the pipeline on disk, the pipeline cache on disk, and use that. And I'm going to save time, effort, energy, etc., efficiency, all of that good stuff. Okay. And that's fine. Everyone is in agreement. But what happens is that sometimes I start to change the specialization constant that I run my script with. So when I change my parameters for the configuration of running my script, notice again, we say that when we input 0, we get 0. When we input 1, we get 1. When we input 2, we don't get 2, but we get 1, which is relatively close. Okay? When we input 3, we don't get 3, but we get 2, which is relatively close. So what would happen is that I would say, okay, listen, the parameter that I have is just run the first two. Okay? Just run the first two elements, right? And literally, it's this guy right here, right? So I just say, okay, just run the first, instead of buffer elements, which resolves to 32, right? Buffer elements resolves to 32. Instead of running buffer elements, which resolves to 32, I'm just going to put, instead of it being 32, which which is what this is, right? Instead of it being 32, which is what the shader is expecting here, because this buffer elements is actually buffer elements count. Sorry for the confusion, guys. That's just how it was made. This buffer elements count is actually what the shader reads here, right? So I say, okay, don't use 32, which is what the saved cached pipeline on disk was built with. I want to just change this value to 2. This is a specialization constant. So I'm changing this value to 2. Well, what would happen is that I change the value to 2. I run my script that basically loads the saved pipeline, and I would still get all 32 elements, right? I'll still get all 32 here and all 30. Like, I'll get the exact same display, right? Output and input and everything, right? I don't want to get into the particulars of the script and what this does and blah blah blah, because then you get into threads and work groups and stuff, right? And then I'm like, well, why is it that when I change this value to 2, that I still get the same output as if I ran with 32? That doesn't make sense, right? Now the thing is that if I change it to like if I change it to 3 or 5 or 7 or 9 or stuff, then it would say, oh, sorry, we can't run the application because um we don't have a pipeline to use. In my particular loading algorithm, I say, listen, don't attempt to compile a new pipeline, right? I put a flag in there that says don't attempt to compile a new pipeline, right? So if the saved pipeline that I have on the saved cache pipeline that I have on disk is not suitable, then just basically tell me that, listen, we can't run this because it violates your rule that you're not going to compile a new pipeline, and we're just going to display that error on the screen, and we're going to exit the application, right? So I would get confused because for some of the inputs, right, for 0 and 1 and 2 and 3, well, no, 0, 1, and I think 2, I would get the output as if it was 32. But then if I input like 4 or any of these numbers or any number that's above 32, I would get an error saying, listen, we don't have a pipeline for this, and we can't compile a pipeline because you told us not to compile a pipeline. And I was like confused, like why are we getting, why am I getting inconsistent errors based on, because there would be like gaps. Like I could do 0, 1, 2, 4. I could do 4, but like 3 and 5 would error out. 6, 7, 8, 9, 10, and 500 and 100 and 35 and 32 and all that would error out. But like, why would 4 run? And basically, it was because of what's happening is that the driver is looking inside of, it's looking at the entirety of the process that we're doing. And it's basically making optimizations, and it's saying, hey, this Fibonacci stuff at 0 and 1, we basically get the same behavior. So we're just going to run with the cached pipeline that we have and then try and make modifications at runtime to, make it right. But it's a very inconsistent and dangerous thing. And as I said, I'm expecting only 1 or 2 elements or like 4 elements, but I'm getting all 32, right? And this is the sin of the driver, right? Because the driver now is looking at our process, looking at the tree of command that's happening on the shader, and then trying to manipulate stuff, you know basically saying, okay, this generic pipeline that we have is good enough for what I want to do, so we're just going to run with it. And then when we run with it, we get basically the same output as if I had 32 here. But I don't have 32 here. I have 1 here, or I have 2 here, or I have 3 here. Or I have 4 here. So 0, 1, and like 4 here, right? but you're giving me behavior as if I did the pipeline as a default of what I saved on disk. So this is a very strange and unusual thing. So in order for me to just do a sanity check, what I ended up doing was changing instead of doing the Fibonacci stuff, I just changed it to the buffer elements, right? So if I input 5 here, I just get all fives. I get all fives here. If I input 31 here, I get all 31. If I input 2 here, I get all twos here. If I input 0 here, I get all zeros, right? I kind of changed it so that there was like a hard line, boundaries between the different values, so that the driver doesn't try to, you know, um, take what was, what is completely incorrect, and patch it up, because the results are small, or it's a small enough change where the driver feels it could just it could just modify at runtime. Strange behavior, guys. Like, I mean, that's the best way I can explain it. But so let us just continue with the plan. Okay, so we have our default file, and we are basically running the we're running our file. Everything is fine. Now what we want to do is we want to um, put some logic in, so that we're saving a cached file. Okay, so I'm going to basically um, take out the default file, and I'm going to put in now a file that what it does is let me just make sure. Right. So I'm going to put in a file now that basically um, right. Okay. So I'm going to put in a file now that basically saves dump cache right after pipeline creation. So write pipeline cache to disk. Okay. So basically now I'm gonna save my cache that I created. I'm gonna save it to file. Okay. I'm gonna save it to file. Okay. So I'm basically the default the default application, it does create the pipeline cache, but it doesn't save it to disk or anything. It just kind of exits with the application exiting after you press enter and blah blah blah. Right? But we're now gonna save our pipeline cache to this file called compute headless cache bin. Okay. So when we run this file, this was for like inflating the number of pipelines, so I could see the file size change for the cache, but we'll get into that later. So I'm commenting on that, right? But all I'm doing now, the only modification is that I'm running the application, but now I save the file to disk, right? So when I run, I get exactly the same behavior. It says road pipeline cache compute headless cache dot bin to 7,820 bytes. It's now saved in disk, right? And I have it saved in disk here, as we could see. So basically, we have it saved in disk here. Okay, so we have basically 8 kilobytes of this saved in disk. Okay, and if I were to just for completeness, if I were to inflate the number of pipelines that I create, the file size is going to change, right? So if I inflate the number of pipelines that I create and then cache, you're going to see that the pipeline, the size of the file changed to a bigger number, right? And we could see that in our compute headless cache bin is now 92 kilobytes. Okay, so you guys get that. But for our intents and purposes, I don't care about the extra pipelines. Just know that when you have a bunch of different pipelines with different configurations and stuff, um, when you want to load a particular pipeline, you still have to act like you're creating that specific pipeline, like you're just creating the pipeline and all that stuff. But then you reference the file, and then what the driver will do, the driver will go into the file, right? So even if it's a big file with multiple pipelines, it will go into the file and try to find a pipeline that matches the settings that you're asking for. It's a very weird roundabout way that it goes about it, but basically the driver goes into that big file with 2,000 different pipelines, and it says, is there a pipeline that matches what you're asking for in your application? Because again, I say you run the program as if you're creating the pipeline with all your settings, and then you reference the file, and then the driver will go into the file and say, hey, is there a pipeline that matches the settings that you are requesting? Apparently this lookup is very fast and efficient, so it's not like if you had a whole bunch of pipelines that it's going to slow down the process because you're searching for pipelines. It's actually pretty efficient, right? But anyway, let's not we're gonna go back to normal. So what we want to do is just create the cache for the one pipeline that we have, right? So we're now back to 8 kilobytes of our cache. We could see here that we're back to 8. Okay, so that's fine. All right, so now we have this saved to disk. Now, just as a sanity check, we also have to make sure for our specialization constant is set to 32. Okay, so we have it set to 32, which is defined all the way up here. We have 32 elements. It's defined as the specialization constant, and what have you. Okay, so now we have our saved uh, pipeline cache on disk, assuming buffer elements count of 32. So now what we want to do is we want to run another application that basically now is only going to run the cached file. So it's going to check if a cached file is available, and if the file is available, it's going to load it, and it's going to use that for our application. Now again, remember I said, when we're running our application, when we're even if we have a cache available, we still have to write out our pipeline and the configurations and everything that we want as if we're just creating the pipeline, right? So we're gonna do that, but then we're going to ask what the driver is going to do is we're going to ask, say, hey, well, I have a pipeline cache available. Let me see. Right, I have a pipeline cache available. Is this the right one? 1 second. Right, so we're gonna now load the cache file that we have on file, and we're also going to put in a flag that says compile. Okay, right. If pipeline compilation would be required, fail. So we're gonna basically load the cache file. We're gonna load the cache file, and we're also gonna put in a restraint that says VK pipeline create fail on pipeline compile required bit. So what I'm saying is that I need to make sure that I'm actually loading the cached pipeline, and I'm not recompiling a brand new pipeline. Okay, so I put in a flag that says, listen, if you're creating a new pipeline, if you have to compile a new pipeline, then you know just put it as failed and let me know that it failed. Okay. So two things again. Number one, we're loading the cached file. We're loading the cached file, and then number two, we're setting up a restraint that says, listen, if we have to compile a new pipeline, stop. If that's required in order for us to achieve what we want to achieve, then stop. Okay. So when we run our application now, we basically get we keep everything as the same as what we expected, right? So we have um, loaded pipeline cache blob, compute headless cache.bin 7818 bytes. Okay. Pipeline created without compilation, cache satisfied. And then we have our input and we have our output. So we basically loaded from file. Okay. We're going to mess around with now the specialization constant, because the specialization constant is going to affect sort of one of the things that sort of makes one pipeline different from another, all of that stuff. All right, let us start from baseline. So we know this resolves to 32, but let's just do a sanity check, and we're going to just put in, instead of buffer elements, we're going to put in 32 and make sure that we actually get the same result. Okay, so we put in 32. What do we get? Loaded pipeline cache blob, pipeline created without compilation. Beautiful. All right. That's what we expect. Now, let us start playing around with this specialization constant. So what is supposed to happen? What is supposed to happen is that this buffer element count here, which actually corresponds to buffer elements here in the shader. Again, it's confusing, guys, but there's a buffer elements up top on the source code on the C++ side, but we don't necessarily care about that. We care about this buffer elements count in the CPU side that corresponds to buffer elements on the shader side. Okay, so what's supposed to happen is that if I change the specialization constant value here to a different number, so let's say 33, what is supposed to happen is that when I run the application, the driver is going to it's going to load, we're acting like we're creating a pipeline with the buffer element count value now of 33. It's going to look into the cache and see that we have a pipeline there. I mean, we have a cache pipeline there. But the driver is gonna say, hey, the cache pipeline settings configuration is different from what I have that I'm requesting for my new pipeline. Since it's different, we're gonna reject the cache pipeline and we're gonna exit the program and say, hey, listen, I know you wanted to build this pipeline with buffer element count of 33. I checked the disk. The disk had a pipeline in there, but the pipeline is buffer element count of 32. It is not 33. And you also explicitly told me don't attempt to create to compile a new pipeline. So there's nothing I can do. You restricted me. The cached pipeline is not valid, right? And I can't compile a new pipeline, so I'm just gonna exit, right? And what happens is that when I run it, that is exactly what happens. So we have loaded pipeline cache blob, compute headless cache.bin, right? Error. VK pipeline compile required. Cache did not satisfy no compile requirement. This is good. This is what we expect. We expected that, right? It didn't fulfill the requirements because I have 33 here. The saved file has 32. It doesn't fly, right? If I change it back to 32 and I run again, I'm going to get you know, pipeline created without compilation, cache satisfied. All right, we're good. We're good to go. If I do 500, okay, what do you guys expect is going to happen? Okay, cache did not satisfy no compile requirement, right? VK compile required, right? So 500 doesn't work. Okay, let's try 30. Okay, what happens? Still, it doesn't match up. That's fine. Okay, if we try 9, okay, still doesn't match up. Everything is going according to plan. Okay, we could try 5. Okay, so we'll do 5, right? Still doesn't match up. We are fine. But here is where the problem comes in. Let's say I do 2. See, now when I do 2, I still get output as if I had put in 32. And the reason for that is because basically the driver is looking like, okay, the first two elements is like similar. So 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, but like basically the first couple of elements is similar in input to output. So this must be a good file. This must be a good thing. Everything is good, which is not true, right? So if I do 3 now, you're going to see that I now get an error. Okay, cool. But if I do 4, I get back the normal 32 output, right? And I don't know, the Fibonacci stuff is just a whole nother cup of tea, which I don't want to bake more confusion into it. If I do 1, I still get that behavior because of the Fibonacci stuff. This is all driver optimization, right? So the driver is trying to basically just patch things up and use the cache pipeline that we have. Even when I do 0, it passes, right? Which is not correct. If I do -1, then it fails. I think for all negative numbers it fails, right? I mean, I guess because it's just such an obvious change, right? So yeah, for all negative numbers it fails. Okay, so we are we sort of understand that logic, right? If I do -32, it's probably going to fail too, right? Because it's negative number, it's not matching up to our cached file, right? So if we put it back to normal, um, we get back our normal thing. Okay, so that's that. So remember now, the driver is looking at this. It's because part of the pipeline cache is also boiling down the shader to spare V and like machine code language, right? So the pipeline cache includes not just the instructions here, but it includes the shader instructions and a whole bunch of other stuff, right? But it's basically trying to hack, looking at input and the output and basically saying, okay, the results are similar. So for these similar things, we're just going to run with what was there before. Don't ask me why, guys. I mean, it's kind of a weird thing, and I don't really the Fibonacci stuff is just, we don't need that complication. So what we're going to do now is I'm going to update the shader file to just say whatever the index value is coming in, output for it the buffer elements, right? The buffer elements that I assign here, right? So it's going to be the same number for all of them. But I can't just change this and save the file. Remember, guys, we have to first of all we have to recompile the shader. So we have to recompile the shader. to spare V format, right? So we have to recompile the shader. Number two, we're gonna have to resave the cache with. Do we have to resave the cache? Do we have to resave the cache? Actually, we don't have to resave the cache. No, we don't have to resave the cache. All I have to do, no, yes, I have to resave the cache. Yes, I have to resave the cache, the pipeline cache, because remember, we now have new instructions on our shader. So not only do I have to recompile the shader to spare V format, but then I also have to rerun my save pipeline cache algorithm so that the new cache has this changed instruction in it in the bin file, right? So we have to recompile, we have to resave the pipeline cache so we get a new bin file with this new instruction in it, right? So let us get to work. So we have to save this. So I'm going to save this, and then I'm going to recompile my shader. So I recompile the shader, right? I recompile the shader. Now I have to put in back my I have to put in back my I have to put in back my save pipeline cache. Let me just make sure. Sanity check. Right. Okay. Dump cache right after pipeline creation. Right. So I have to save this guy now. So let us do that. I mean, let's run this. So we're gonna run this. Okay. And actually, when we just do the raw run, we run our application, and then of course we save the pipeline to cache and all that, but we already get the new results, right? So basically, as I said, whatever count is, which is buffer elements, which is 32, we're just going to output that basically as the result. For every input is just the same result, okay? The reason I do this again is just to have a hard line, so the driver doesn't play games with the logic, right? So now I have an updated file. Notice that the date of it changed, and even the size of the file, actually it went from 8 KB to 7. I guess it rounds up, right? It rounds up. But we had 8 before, now it's 7 with just this minor change of the logic, right? Don't ask me why, but change of logic, we get a smaller cache file, right? Cool. So now what we have to do is now we have to put back in our load file, right? We're gonna put back in our load file. So we're loading now from from disk. So again, we have compute headless cache bin pipeline created without compilation, right? So we have our input and we have our output, which tells us that the cache file now has a new instructions, right? Output the thing. So again, I do this to enforce a hard line in terms of any little change in this is gonna the driver is gonna see that it's a different change. So if I do 32, let's just make sure that we're on the same page. If I do 32, we get the load was successful. The load was successful. No problems, right? Load was successful. If I do 33, just like previously, we get load was not successful, okay? And then of course if we do 500, load was still not successful. That's in line with the previous results, right? In line with the previous results. Now if we do 1, These should all fail now. These should all fail. There should be no holes in this. So one fails, let's do two. Two fails, let's do three. Three fails, let's do four. I think four was the one that the driver saw as similar. So they all fail, guys. They all fail. Five fails. Let's do nine. Right. So the driver now says, listen, this pipeline is not the same as what we previously had saved. Right. So there's now a hard line. Again, the reason that we do a pipeline cache is because to we want to save on the pipeline compilation, right? So, obviously we have a very simple example here, but if your pipeline gets very complex and there's a lot of settings and stuff, now we're back to normal, right? If there's a lot of settings and things of that nature, we're going to hit up on problems as it relates to, um, just the speed of the application and all of that stuff. Like AAA games use this a lot apparently. They save the pipeline caches and stuff so that the frames per second doesn't fall too much and the games run smoother. And that's pipeline cache, guys. So this was our lesson in terms of pipeline cache, loading from file, and the dangers of, you know, like I said in some of the other videos, the driver is the middleman and the driver, touches the hardware. So really and truly you're at the whims of the driver, and this could be a huge bug because you might think your logic is different enough or whatever, but if the driver doesn't think so and it gives you the same behavior as what you weren't expecting, then there is a problem. um, it's all in the name of optimization. The driver wants to make things efficient, but sometimes it messes up how it goes about doing all of this stuff. And I can't, the Fibonacci stuff. That's just what it does, right? So that's the final discussion on pipeline cache. I think I've exhausted this enough. Um, yeah, so specialization constants are part of pipeline identity. The pipeline cache keys on shader module, entry point, specialization constants, pipeline layout, descriptor layouts, relevant driver state. Um, yeah, and so that doesn't necessarily mean, um, yeah, it's just a weird thing. But at least we now have an idea of pipeline cache, saving it to file. Um, the fact that it can help us. It's a tool that you could use to help you get get your application running faster. And also remember, guys, specialization constants is commonly used to you know for you to exert control over how your shader behaves, right? So even with this, we have this if statement where we're testing against this value here, which is this guy right here, right? So just something to keep in mind. um, and yeah, guys, this is CUDA Education. If you want to follow along with this stuff, tutorial number 1 is installing the Vulkan SDK. Tutorial number 9, in tutorial number 13 is installing all of these examples. It assumes you have a Windows machine with a Vulkan-capable GPU. If you want to run the ray tracing stuff, you have to make sure, because the examples have some ray tracing stuff. This is not a ray tracing example, but if you want to run that stuff, you have to make sure you have a ray tracing capable GPU. For NVIDIA, it's RTX and above. I don't know about Intel and AMD. I know there's a new generation of GPUs coming out from Intel, so I believe all those new generations would be ray tracing capable. Not sure what's going on with AMD, but yeah, guys. Tell your friends, like, subscribe, share the video. Thank you for watching. Have a great day.